So this video is about polyprotic acid and base equilibrium, an introduction to the topic. So you remember that according to Bronsted-Lowry, acids and bases are proton donors or acceptors, right? So H plus again is our proton, that's the sort of acidic species. And so we're sort of transferring those protons back and forth, and that's sort of the characteristic of acid and base reactions. So what does it mean to be polyprotic? Well, that prefix poly means many. So polyprotic simply means that you can donate or accept more than one H plus ion. So let's look at some examples of an acid. So this is phosphoric acid. And phosphoric acid has 3 hydrogen atoms attached to 3 of the oxygen atoms of the phosphate polyatomic ion. And each one of those H pluses could possibly be donated to another molecule. So we would say that phosphoric acid is a triprotic acid, meaning that there are 3 donatable protons. And so we can imagine that this happens in steps. And so when you add this to water, we can think about how easily it donates each successive proton to a water molecule. So remember, we always tend to compare how strong an acid is by thinking about how easily it can donate a proton to water. Similarly with bases, we'll think about how easily it could take a proton from water. So this again is going to be an equilibrium reaction. And so when we transfer a proton over, we'll end up with our H plus species, the hydronium cation. And then we just remove one H plus from the formula of our compound, so that's just going to give us 2 hydrogens in this case, H2PO4. And then we make the formula less positive by 1. So we started out with a neutral compound, so now it's going to be -1. And like usual, we can write down an equilibrium constant for this reaction. So a Ka for the acid dissociation reaction. And again, it's products of a reactant, so it'll be the concentration, the molarity of our hydronium ion, the molarity of our dihydrogen phosphate anion, divided by the molarity at equilibrium of the phosphoric acid molecule H3PO4. Remember, we don't include the water because it's a pure liquid, and when we account for standard states, it divides out of this expression. So because this is the first proton being donated, out of a possible 3, we need to keep track of that. And so we're going to add another label to our little subscript here. We're going to call this Ka1. So 1 is for the first proton being donated. But we can imagine that a second proton is donated by starting with this species. So now we're going to start with our dihydrogen phosphate anion, H2PO4. And we're going to imagine that it donates a second proton to another water molecule. So a proton will come off. We'll end up with yet another hydronium ion being produced in the solution, H3O plus. And then what do we get when we remove one proton? We'll just have one H, PO4, and now there's a -2 charge on that anion. And so there's an equilibrium constant for this reaction, of course. We could write down a Ka, and since we've donated now the second of 3 protons, we're going to call this Ka2 for the second proton. And so its equilibrium constant, H3O plus HPO4 2 minus divided by the concentration of H2PO4 1 minus, right? So that would be our equilibrium constant expression. And let's do this one more time for the last proton coming off. So we'll start, again, we do this kind of successively in steps, right? So one at a time. So HPO4 2 minus donates yet another proton to water, and I'm going to leave off my phase labels just to make this a little bit quicker, and we're going to get H3O plus. And what do we get when we remove one more proton from the phosphate there? We just get phosphate, PO4 3 minus now. And so there's going to be a Ka3 for that, and so that'll be the equilibrium concentrations of hydronium phosphate divided by the equilibrium concentration of the hydrogen phosphate anion. All right, so there's our 3 Kas. Now it turns out because of electrostatics, right, we've removed one proton, but now when we remove the second proton, we're pulling something off that has a positive charge, and we're moving that from something that has a negative charge, right? So the hydrogen ion has a +1 charge, And we're trying to take that away from something that already has a negative charge. So you'll remember electrostatics that plus likes minus, and so it's going to become progressively harder and harder to do that. So it is normally the case that our Ka1 value is bigger than our Ka2 value, which is bigger still than our Ka3 value. So that's a typical pattern that we will see in polyprotic acids, that the successive acid dissociation constants get smaller and smaller and smaller. So what is that telling you? That's telling you that that acid gets weaker and weaker and weaker, that it's less and less likely for that ion, for that acid to donate its proton. So this guy, acting as an acid, really doesn't do that very much. So it gets progressively weaker as we go down this line here. So we can think about bases as well being polyprotic. So oftentimes bases will be anions, polyatomic anions. There are common bases that we look at that are polyprotic. So we're going to imagine phosphate here, right? Phosphate is the conjugate base, so our Cb of the acid HPO4 2-. So what if it were to act like a base? So what if it were to act like a base? So let's do that reaction. So remember, there's a base hydrolysis reaction. So we are going to imagine that we start off with some phosphate. So maybe we get that from like sodium phosphate, for example. And it's going to react with water because we've dissolved it in some water. So now this is acting as the base. That means that water is going to act as the acid and be the proton donor in this case. And so we're going to take a proton away from water and stick it on to the phosphate. And so what do we get? We get HPO4. And since we've added an H+, the charge is going to get more positive. So we've just got a 2- charge. And that'll still be aqueous. And then we've made the hydroxide ion, OH-. So phosphate is a triprotic base because it can take as many as 3 protons away from water until we've neutralized that full charge, basically working our way back up to the H3PO4 phosphoric acid molecule. So as usual, we can write an equilibrium constant for this reaction. And because this is a base hydrolyzing water, we call it a base hydrolysis constant, B. And since this is a polyprotic base, it's taking away its first proton, so we call that B1. And again, we can write this down, products over reactants. It's HPO4 2-, concentration at equilibrium divided by the equilibrium hydroxide concentration. Remember, there's just one of those in solution, even though we might write like hydrogen ion concentration multiple times, there's only one of those concentrations in any given solution. And then we would divide that by the equilibrium phosphate concentration, right? So that would be our Kb1. So similarly, just like we did with the acid, we can work up in steps, taking away a proton from water in steps for this polyprotic base. So HPO4 2- now yanks another proton off of another water molecule, leaving off my phase labels. We'll get H2PO4- plus another hydroxide. And now there's an equilibrium constant that we call Kb2, the second base hydrolysis constant. And so that's going to be H2PO4 equilibrium concentration times the equilibrium hydroxide concentration divided by the equilibrium hydrogen phosphate ion concentration. That would be our Kb2. And finally, we would have our last reaction where we start with the dihydrogen phosphate anion, H2PO4, and it yanks yet a last proton off of a water molecule to make the phosphoric acid molecule, H3PO4, and yet a final hydroxide. So that's why phosphate we can think of as a triprotic base, because it can take away as many as 3 protons from 3 different water molecules. And so there'll be a third base hydrolysis constant for phosphate, and so that'll be the concentration at equilibrium of the phosphoric acid, H3PO4, times the hydroxide ion concentration, divided by the H2PO4- concentration at equilibrium. So those are our equilibrium constants for all of these reactions. So an example of a triprotic acid and a triprotic base. And you see that there's kind of a relationship here. So let's check that out. So for example, this reaction right here, and if we scroll up a little bit, this top reaction that we wrote down, this one right here, they have some chemical species in common. let's go ahead and label those. So what they have in common are the phosphoric acid, H3PO4, and the H2PO4 minus species, all right? So these two species show up in this reaction, as well as this reaction down here. And what we know about those species is that they represent a conjugate acid-base pair. Right? So that's a conjugate acid-base pair. So if we think about the equilibrium constants for these reactions, we discover something that's kind of interesting, right? So if you take the Ka1 from our top reaction up here, so the one that I put in the box up at the top, that Ka1 expression, and we were to multiply that by the Kb3, what would we get? Well, let's write down those equilibrium constant expressions. Remember, our Ka1 is going to be H2PO4 minus times the H3O plus concentration divided by the H3PO4 concentration, right? So let's scroll back up and just confirm that. Yep, there it is over here on this side, right? So right there is our Ka1 expression. And so we want to multiply that by the Kb3 expression, which is, right here. So we're going to multiply that by Kb3, which is the H3PO4 concentration times the concentration of OH minus divided by the concentration of H2PO4 1 minus. Now what you'll notice is that when we're multiplying these two together, that we have an H2PO4 minus up here in the numerator of the first term and in the denominator of the second term. So when we divide those out, right, they cancel. We get 1. And the same thing happens with the H3PO4 on both sides of these. And so what do we end up with? We end up with just H3O plus times the OH minus concentration. And from other things that you've learned, that should look familiar. This is our water hydrolysis constant. So Kw is equal to the product of these two equilibrium concentrations. So it turns out that when you multiply the acid and base dissociation constants for the first acid dissociation and the third base dissociation, because those are the two that relate these two species, that you get Kw. And we could go through and show that there are other relationships that hold true here as well. So if we look at, for example, Ka2, and we were to multiply that by the Kb2, they relate these same conjugate acid-base pairs, the H2PO4 minus and the HPO4 2 minus, right? So those are the conjugate acid-base pairs in these reactions. So if we were to take Ka2 and multiply it by Kb2, we would see that that also equals Kw. So that's an important connection between these equilibrium constants that we will use later on. All right, so just keep that in mind. So there's a little bit about polyprotic acids and bases and their equilibria.